Pluto's atmosphere is far colder than scientists once expected, and for years, nobody could fully explain why. Then the James Webb Space Telescope looked at Pluto in infrared light and helped confirm an idea that had once seemed surprisingly unlikely. Pluto's high-altitude haze may be playing a major role in controlling its climate. The story begins with NASA's New Horizons spacecraft, which became the first mission to explore Pluto up close in 2015. Scientists expected a cold, distant, relatively simple world. Instead, New Horizons revealed towering mountains made of water ice, enormous plains of frozen nitrogen, complex surface chemistry, and a thin bluish haze extending high above the surface. But one of the biggest surprises wasn't something scientists could see in an image. It was Pluto's temperature. Atmospheric models suggested that Pluto should have been significantly warmer than the measurements indicated. The difference was roughly 30 degrees Celsius. That was far too large to dismiss as a minor measurement error. Something in Pluto's atmosphere appeared to be removing energy far more efficiently than existing models could explain. Researchers spent years checking the observations and refining their calculations. Eventually, an intriguing possibility emerged. What if Pluto's haze wasn't simply a layer of particles floating through the atmosphere? What if the haze itself was helping cool the entire world? In 2017, Planetary scientists proposed that the microscopic particles making up Pluto's haze could absorb sunlight and then release that energy as infrared radiation. Instead of simply reflecting or scattering sunlight, the particles could effectively act as tiny thermal radiators, sending energy directly into space. If that mechanism was real, it could explain why Pluto's atmosphere was dramatically colder than conventional models predicted. The idea also produced a testable prediction. The haze should emit infrared radiation at specific wavelengths. The problem was that detecting such a faint signal would require an extraordinarily sensitive instrument. That instrument eventually became available aboard the James Webb Space Telescope. Webb launched in 2021 and began scientific observations in 2022. Its mid-infrared instrument, or MIRI, was particularly important for this investigation because it can detect thermal radiation at wavelengths that are difficult or impossible to study effectively from Earth's surface. Researchers eventually directed Webb toward Pluto and its largest moon, Charon. This was a major technical challenge because Pluto and Charon appear extremely close together from Earth. Earlier infrared observations could detect radiation from the Pluto system, but separating the individual contributions from Pluto and Charon was much more difficult. Webb's sensitivity and resolution made that separation possible. By observing the system across multiple infrared wavelengths, researchers were able to distinguish Pluto's thermal emission from Charon's. What they found supported the basic idea that Pluto's haze is not merely a visual feature. It is an active part of Pluto's energy balance. The particles in the haze can absorb incoming solar energy and radiate energy outward in the infrared. That process allows heat to escape into space and contributes to the surprisingly low temperatures observed in Pluto's atmosphere. The particles themselves are known as tholins, complex organic compounds produced through chemical reactions involving methane and other molecules under ultraviolet radiation. High in Pluto's atmosphere, sunlight drives these reactions and gradually creates increasingly complicated hydrocarbons. The resulting particles become part of the haze and slowly settle downward. That gives Pluto a remarkable atmospheric cycle. Sunlight drives chemistry. The chemistry creates particles. Those particles form the haze. And the haze helps Pluto lose energy through infrared radiation. In other words, microscopic particles may be influencing the climate of an entire world. That is what makes Pluto so scientifically interesting. The discovery also provides clues about the relationship between Pluto and Charon. Methane from Pluto's atmosphere can escape and move through the Pluto-Charon system. Some of that material can eventually reach Charon's surface, where ultraviolet radiation alters the molecules and helps produce complex organic compounds. This process may contribute to the reddish material seen around Charon's north polar region. So Pluto and Charon aren't completely isolated worlds. Material can move from one to the other, linking their surface and atmospheric chemistry across enormous distances. The implications may extend beyond Pluto. Scientists are interested in whether similar haze-driven processes could occur on other cold worlds with nitrogen and hydrocarbon-rich atmospheres, including Saturn's moon Titan and Neptune's moon Triton. Titan is especially interesting because it also has a thick atmosphere filled with complex organic chemistry. Its environment is dramatically different from Pluto's, but both worlds demonstrate how sunlight can transform simple atmospheric molecules into increasingly complex particles. There may even be lessons here for understanding Earth's ancient atmosphere. Long before modern Earth's atmosphere became rich in oxygen, our planet had a very different chemical environment. Studying haze formation and atmospheric chemistry on worlds such as Pluto could help scientists investigate how organic molecules behaved under conditions that were very different from those found on Earth today. Pluto itself has already demonstrated how misleading first impressions can be. When Clyde Tombaugh discovered Pluto in 1930, it appeared as little more than a tiny point of light. For decades, telescopes could reveal almost nothing about its surface. Then New Horizons changed everything. The spacecraft launched in January 2006 and spent more than 9 years traveling toward Pluto. In July 2015, it finally reached the dwarf planet, passing through the system at high speed and collecting an enormous amount of data during its brief encounter. New Horizons revealed that Pluto was anything but a dead frozen rock. Its surface included vast nitrogen ice plains, enormous mountains of water ice, glaciers, complex atmospheric layers, and evidence of geological processes that have shaped the surface over time. One of the most remarkable regions was Sputnik Planitia, a huge basin filled with nitrogen ice. Pluto's mountains were equally surprising. Because temperatures on Pluto are so low, water ice behaves more like solid rock, allowing it to form enormous mountain ranges. And above this strange landscape was the haze that would eventually become central to the climate mystery. Pluto's atmosphere is extremely thin and changes over time. Its long, elliptical 248-year orbit around the Sun causes its environment to evolve dramatically. When Pluto moves closer to the Sun, sunlight can warm surface ices enough for nitrogen and other materials to transition directly from solid to gas. This can temporarily increase atmospheric pressure and density. As Pluto moves farther away again, atmospheric gases can cool and condense back onto the surface. New Horizons arrived relatively soon after Pluto's closest approach to the Sun, giving scientists a snapshot of an atmosphere that was comparatively active. Webb now gives researchers another way to study that atmosphere remotely. Instead of relying on a single brief flyby, astronomers can observe Pluto repeatedly and examine its thermal behavior over time. That difference is important. New Horizons provided unprecedented close-up measurements of Pluto's surface and atmosphere, but the spacecraft passed through the system only once. Webb can return to the same distant target and observe how its infrared properties change. MIRI is particularly valuable because it observes thermal radiation at mid-infrared wavelengths. The instrument can detect incredibly faint heat signatures from distant objects while operating in the cold environment of space. For Pluto, those measurements allow scientists to study subtle differences in thermal emission from the surface and atmosphere. Researchers can compare observations taken at different points in Pluto's rotation and use them to investigate temperature, surface properties, thermal inertia, and atmospheric effects. That is exactly the kind of observation needed to investigate a climate mechanism that cannot simply be photographed. The story becomes even more interesting when Pluto is compared with Titan. Titan has a much thicker atmosphere and even has lakes and rivers of liquid methane on its surface. Pluto is smaller, colder, and has a much thinner atmosphere. Yet both worlds contain atmospheric hydrocarbons and complex organic haze particles.